Thank you. Thank you, everyone, for joining this meetup. Today, we are going to discuss all about the agent lightning. That's one of the latest framework from Microsoft Research. And what we do is we will set some foundation for first 30 minutes, and then jump into the paper reading. So it has two parts. All right. I mean, some of you joining may not be familiar with the concepts listed in the paper. It's a good idea to introduce some concepts and then some examples, and then jump into the paper reading. That way, we can cover some of the different audiences joining this meeting. In case if you're already very familiar with this concept, and then if you're only looking for advanced sort of the aspect of the paper, please be patient for the first 20-25 minutes. So I'm looking at the audience here. There are probably more than 7 or 8. Thank you for joining. And I assume some of you already familiar with this agentic AI. And then as part of the agentic AI, and now we are all talking about how to fine tune what we call AI agents. So this topic do need some background understanding. Hopefully you're familiar with basic RAG development, and then followed by the agentic AI development. At least at this very beginning part of the agents development, because this paper goes into much deeper how we can improve AI agents, some of the decision making process, recommendation process. So that's where what we call fine tuning the agents, or fine tuning the LLMs used by the agents. What are the different approaches, and why this lightning approach is very handy and powerful. So this comes under the domain of fine-tuning the LLMs for agentic AI reasons. So obviously the foundations need to be already familiar before some of the concepts listed and the ideas listed in the paper. So I'm hoping that you have those foundations. But I will go through some of the foundations so that we can quickly wrap up and then go into the paper more details. So that's the idea. Now, again, today, actually, this paper needs 2 sessions. First session is about introducing the paper. As a companion to this session, we also have a code walkthrough. There is a good code, sample code developed by the Microsoft Research, and we can go through in some other session, maybe in next week or the following week. So with that said, let's start from some basics here. As I again said, right, first 20-25 minutes is about introduction, and then we go into the paper. So during the paper reading, I do know that some of us, you commented last time, you wanted to see more critical analysis. I'll try to do my best on that. We look from multiple angles and multiple thought process, and ask some critical questions, and then validate some of the paper's assumptions, and then the testing and background and their benchmarking. We'll do that as part of the paper reading. So let's start with the problem. Let's start with some imagination, how we are going to build the AI agent. And of course, if some of you want to pause me, once in 5-10 minutes, once in 10 minutes, you can always pause and ask question. I will also try to pause if I watch my time. Then ask for any clarification you need or any questions you may have. So imagine every 10 minutes, I'll try to do that so that I continue the flow, but also take a break and then look for your questions. I also look into the chat right now. There is let's see what's the question. I mean, right now, Sam has sent that. Thank you, Sam. So you can always interrupt me every 10 minutes and then we'll pause and answer. Okay, the first thing we want to do is think about, we are going to develop an agent, AI agent, right? So now you probably might be using some agentic platform to develop such agent, right? Probably Crew AI or LangGraph, and then A2A. These are all the platforms to develop. So let's ask a question. We want to develop an AI agent where we want to ask questions like this. Book me a flight from New York to Paris for under $800 next weekend. So that's a question, the AI chat bot, you're typing that question. Now, what do you call agent? That agent is supposed to do a lot of things here. It's supposed to figure out, the tickets under $800 between these source and destination, and also it has to look at the calendar, and then figure out, and then of course later, it has to book it. So the right now the question is not to. It also has a book, so it has to figure out and get the confirmation from the user and then book it. You see, there are a lot of steps involved in that. It's not a simple RAG question, right? It's called agentic RAG, you can call if you want. And then it has to use some tools to figure out this flights, and it has to reason to understand through all the possible flights which one could be the better, and then it has to do multiple steps. So there is a multiple steps involved in this answering this question. So it is definitely a complex steps involved in that. There are so many corner cases that make this can be failure. And then there are so many what I call unexpected situations. Like for example, based on the context you may have during the discussions with the agent, you don't have for example, some of us may have a need to book check-ins, right? Some of us don't need to book a check-ins. A lot of these preferences and then context, you may have preference to be at the window seat. So the user's preference seats and then context and history need to be applied in conjunction with multiple steps needed for these agents to answer it. So that's a starting point. Now we'll come to a place where I will tell you why the fine tuning is necessary. Uh, just to get the audience pulse. If any of you are not fully into any of you are not into the agentic AI, please let me know. So I just want to get the poll. And I assume all of you have some introduction to the agentic AI. If not, at least I know some of the audience don't have that, right? Okay, so I think Sonia probably not having the agentic AI experience. But okay, it's the example.
Sorry, Krishna. It's the other way around. I'm very well
Okay,
aware of what agentic
all right.
AI is.
Okay.
Please go ahead.
Yeah, me too.
Okay. So at least I see two or three, so far responses. Good. Thank you. So, but let's start with the introduction, right? I mean, in the sense example here. This is what are we trying to build? We are trying to build the agent for this, right? We talked about that. It needs understanding, it needs reasoning, it needs to use tools, and then it has to have some way of decision making. Well, as we know, this is not a simple process. There are multiple complexities involved. We talked about that. The architecture some of you might be using today is AI agent using Crew AI line graph, right? It uses the LLM as a brain, and it uses tools to access all these aspects of the flight finding and booking. These are the different MCP tools you can call. And then we may be using OpenAI or Gemini or even local LLM. You might be doing that. In this context, we are going to assume that we are using some kind of a local model, DeepSeek or Qwen, something like that you are using, because we are going to train the model, right? The context of the paper is to train the model. Generally, it's called, the words that we use, we call LLM agent. When we hear about LLM agent, it's nothing but an agent using the LLM is called LLM agent. So we are going to train the LLM agent now. Again, when we always say training the LLM agent, it means your local model. That's a context here. Okay, so this is a local model, and then this is a tools used, and this is a first way of thinking. We are going to write an agent, we are going to create a prompt, and then making this work. So you're going to code either you as a, you can write your own agentic program. You don't need any other framework, but you can use framework like LangChain, LangGraph, Crew AI, and implement all these things. That's great. The results would look great, and then let's say you completed it and it seems to be working, and your agentic AI is perfectly doing the booking, things like that. So what's the problem with that, right? This does not seem like we need a fine tuning the LLMs. It seems like a simple task, though there are multiple steps. but still it can be achievable without any fine tuning. Um, I know this is an example, but in real life, the situation is much more complex. It's not about 3 step or 4 step. But even within that, you would say that why sometimes fine tuning makes sense. Why is that? Let's pause and ask the question. As your agent is more and more becoming complex, you probably write your agent in prompts. And I have seen in my company the prompt going to 2 pages, 3 pages, because we try to put all the intelligence, reasoning, and then things like that into the prompt. You tell the LLM to be a constraint, you tell LLM to reason, and then you're trying to put the LLM, reason through all the intelligence you needed to build in that agentic AI sort of a workflow automation. It has its own problems. Sometimes context limit may come in. Sometimes, because the LLM by nature is a stochastic machine, it might be answering a little differently every time. In order to fix that, you will force LLM to answer in a certain way. You put some constraint, either using the guardrail or within the prompt itself. You do all kind of magical stuff today, right? We call workarounds. We think prompt engineering is the best thing to do, but we make an workaround and then create the application working for us. What's the problem, as we are encountering? This is a problem. All right, in any we don't know whether this prompt is going to work perfectly in the future, even with the same LLM, DeepSeek or Qwen, or if you move to a complete different LLM, it might break. So these are all the issues with the prompt based approach to have an intelligence in the LLM agents. What's the alternative? Alternative is, why not we have an idea to fine tune the LLM when things reasoning is more, and then the data distribution is not available in the original LLM. You have internal data or custom your enterprise specific data. So there are many other reasons when fine tuning would be make sense. Anyway, today I'm not going into the details of when do we need to fine tune, when do we need prompt engineering is just enough. So that's a separate discussion. But imagine for a while we are decided that fine tuning makes sense for this use case. So that's kind of the assumption we are making for this presentation. Once we decide that fine tuning is needed, now, oh yeah, before that, the core insight is, it's a good analogy. You might want to remember that. If you're, a little bit wondering about fine tuning versus sort of the prompting, here is a good metaphor. Suppose you're, somebody joining your company, right? You're saying on the first day, read the manual of some process. And then, if that person has to read that manual every day and then do the work, that is a prompt engineering. On the other hand, that person learns on the job, talks to other people in the company, figure out the correct way to do things. Then still the manual may be needed, but that's probably the secondary, right? They in their mind they fine tune the working and process. I like this analogy, so you may want to keep that for your reference between the fine tuning and then prompt engineering. All right, so
I have a quick question here.
yeah.
Now, why not use RAG? Because fine tuning can be expensive also,
Yeah.
right? And time consuming.
Correct. So here it is, though in this example, RAG is not there, it is going to tools for all the purpose. Yes, your question is for enterprise data, there may be a RAG, right? You're basically RAG is an extension of getting the context and then prompt engineering, right? That's why it's called RAG, retrieval
Exactly.
augmented generation. Yes, now the question is, why do we need to, between the RAG/prompt based implementation versus fine tuning, right? Why do we need to do that? So that is definitely a question comes to, not only to the beginner, also to the expert in this area. But I'll give you a quick answer. The one of the answer is, if your model don't have the data distribution of the enterprise data, along with that, some of the reasons mentioned here, right? It means when you use a prompt engineering, which is a RAG-based prompt engineering, you still have all these limits. When you're trying to impose, if it's a simple question, RAG is no problem. But when you're trying to impose more reasoning, then prompt will have the same problem. The RAG plus prompt will have the same problem. as more and more reasoning comes into your intelligent decision, and then more and more that reasoning steps or reasoning logic is not available in your the LLM that you are choosing, then at the time fine tuning will come into place. So it's like an escalation ladder. Now we had to start with the prompt, then think about fine tuning, right? If the prompt has an issue, only if it has an issue, now you're asking what are the issues, right? These are all some of the issues. Once you decide that RAG plus prompt based approach has limitations and not working consistently, struggling for to get the right answers, then you think about the fine tuning. So that's called escalation ladder. So that's a quick answer, but there are detailed mathematical answers also there. Then we are talking about probability distribution of your data set, right? In the current LLM, may not be work in your favor if you use prompt engineering, but or on the other hand, you change the probability distribution of your LLM. Now we are getting into the mathematical aspect of that. So that's a good question, but it has many answers to that, and then it's a deep question as well. But for today's purpose, we are not going to attack that problem, right? We assume there is a fine tuning needed. Many people are doing it, but many people are overdoing it, right? Where there is things are needed to fine tune, people are overdoing it. So that's a separate question. Is it okay? We can park that question for a moment.
Thank you.
Yeah. All right, so now we decided that fine tuning is important. Now the question is, how do we fine tune the LLM agents, right? I mean, there are many techniques. One is a supervised SFT technique, and one is RLHF technique, so DPO. So these are all techniques used in foundational model training also, right? You might have heard about OpenAI, DeepSeek foundation model, and then their training pipeline. The foundational model, they have pre-trained model, and then they have the foundational model. So they use such techniques to train and then release the OpenAI models, right, as well as other models. But the same idea is used for enterprise level. The same idea, the process and pipeline could be used to fine tune your own agents based LLM or LLM used for your agents. These are the techniques. Again, it's a big topic. I'm not going to dwell into this topic. That's not the scope of this, but I'm just giving an idea. There is an SFT based fine tuning. There is a RLHF based fine tuning. There is a DPO based finding. Today's paper is coming in this. That's a context. Today's paper is going to focus on agent lightning is a framework or approach to do GRPO based fine tuning. So that's why, when in the beginning of the call, I said, this advanced paper for some, if already they are familiar with fine tuning, they can quickly go into this. But people are coming, into that agentic AI and then getting introduced to the fine tuning. This is an involved paper, right? But I'm trying to help here out. For example, in my company, we are trying out these things because we do see that the need of fine tuning a lot of our small LLMs. Okay, so that's the idea. So how much do we need to know in order to understand this paper, right? Well, I can a little bit go through that. Some more details about this, just for the interest. I'm looking at the time, 7:28. So I can spend another 10 minutes on these methods and then get into that. Okay, what is the next one? Let's me go here. 1 second. I mean, that's a little outside the scope, but I think since one of you asked the question, let's see. Okay, so what I want to quickly point out is some of you are wondering what is SFT fine tuning means, right? I mean, it gives introduction, very good background before we jump into the agentic lightning based fine tuning. So the SFT based fine tuning, you are giving actual hard examples, basically saying you're tagging, right? In traditional ML, we used to say that we have a model. In order to train the model, we are going to tag it, right? Or provide the answers to that, the questions for that model. In a similar way, it's a supervised. So you come up with now we are talking back to the examples of booking the flight. For a moment that you are finding out your agents are not booking properly, your agents are getting confused, and then it's not having consistent response all the time. For whatever reason, now you are going to enforce the model, saying that if you are going to book like this, and then here is the output we want. So, this is a very expensive way of fine tuning. This is an expensive way of improving your model's reasoning capability or answering capability. And why? You may need to come up with a lot of examples, for your applications, maybe thousands of examples, and then do the SFT based fine tuning or SFT based training. So again, let's not go into detail, but in the SFT, this is the process. You take thousands of examples and then use the cross entropy loss, and then you change the neural network model of your LLM. So these obviously, there are pros and cons. As you could see, that is easy to implement because for your enterprise, in this case, for booking the application, you come up with thousands of examples. In your enterprise, you may also have a similar need, but it's a very manual, right? A lot of human effort is needed. So it's not a scalable approach, but it is an approach. People are using this approach. The other approach is a reinforcement learning from human feedback. Okay, I don't know how many of you are familiar with this. Let me pause the question and ask. Again, if you are familiar with all the DPO or LHF and stuff like that, please raise your hand. Otherwise, I assume you guys are not familiar. Any of you are heard about these things, are familiar
Yeah,
with this?
it's what ChatGPT uses. It's the technique that when it asks you which one is better, that's
Yeah, correct.
reinforcement feedback.
Exactly. That's a good point. Yeah, that's what's happening. It used to be a lot last year, but nowadays I'm not seeing much. Maybe, during the 4 and 5 times GPT, it used to ask me a lot, but it's kind of reduced recently. Yes, exactly. So what they're trying to do is they are trying to figure out you to label it as a user. And then, there are techniques, they throw the option, right, to the users. In this case, for example, if your model can respond, your agentic AI can, sometimes it's, randomly it can do it. Randomly for some of the users, it will say, I have two options, and then response A and then response B, and it will ask you to choose what is best for you. And then what it does is then it creates something called reward model. Again, this is one of the technique, very well-known technique. And then using the reward model, they are going to train it. Again, without going into detail, just understand that RLHF is another technique to fine tune your LLM model, which many people still uses that.
I have a
Again,
quick question about that. If there's time. So recently I learned that in reinforcement learning models, it does propagate a network with weights. Even
yeah,
so is that also the case here for
yeah. In every model, it propagates weights, right? Even though I didn't say that here, even gradient descent, even SFT, right? It upgrades the weights. So
Yes.
at the end of the day, any training has to go and change the weights, right? I mean, yeah, true. So SFT also updates here, and then even if you hear it up, they didn't say that, but it updates. PPO updates. That means it's basically internally the model gets updated.
Makes sense.
So yeah. Similarly, there is another technique called DPO. Here what they did is it's better, they figured out even this, PPO is a lot more work, right? They had to, get the, answer collected from samples. But the technique is called DPO, direct preference optimization. Here, with the limited, they don't go to the users and ask, and then they come up with what we call, based on some options, they decide it. So, this is another approach. We will deal with it later right now, but this is another approach. Right now, let's go to the approach that we are going to study. So the approach we are going to study in this paper called GRPO. So GRPO is a technique used in DeepSeek. If you have attended some of the papers on GRPO, that explains how GRPO or how DeepSeek achieved the foundational model training with very limited resources. I mean, they didn't have many people to do SFT. they didn't have many folks to do RLHF. So they really used the technique called GRPO. So the paper is not going to be go much deeper into GRPO, but what the paper is about, a framework which enables practitioners like us to implement the GRPO, right? That's an objective of this paper. So again, the goal of the paper is to see how we can apply the GRPO based training, which DeepSeek familiarized, to your local LLM model. Why do we need to do that? There is no human label is involved. That's that's very interesting. And then there is a design for agentic workflow. So I'm going to cover that. So this is particularly true for the agent lightning based approach. And then it's a framework agnostic. Okay, that's a key thing. So now this technique or this choice or this option called agent lightning with GRPO is the one of the ultimate training technique available today for training your LLM. So that's a statement is paper is making, right? We are going to, of course, ask, look at the benchmark and ask some critical questions about that. But that's a claim from the paper, right? And that's where we are starting. We are setting the context here. All right. So with that said, let's go into the next one. So now we set the context. What did we say that we said? In some cases, it's better to train the LLMs. Of course, it's the local LLMs that your AI agents are using. In that, there are many techniques, but this technique, agent lightning, is one of the interesting and then more recent important techniques. Okay, now we are going to take example, because this example is going to be used, same example I talked, to illustrate the agent lightning. So before we start, what is agent lightning, right? So now you got introduced to the problem setting. Now what about the agent lightning? Let me just make sure I get the right file. Okay. What is agent lightning? So 1 second, this may not be the one. I mean, I'm sorry. So I just need to get the right, 1 second. Okay, it could be that. Okay, 1 second. I'm going to find out. That's not the one. I'm sorry. Maybe this is the one. Okay. All right, here is the one. So what is the agent lightning? Is about the following. So now, how do we introduce, this is not a agentic lightning. This is a regular way of developing an agent. How do we bring in the a lightning concept illustrated in the paper? So now what the real theme behind that is, if you heard about, a little bit story here, if you heard about how agents, how the observability works, if you are used to Python, if you are used LangChain or LangGraph or CrewAI, and if you have implemented the observability, in other words, how the LLM calls are made, usually you use a library. You might use Arise library or Ragas library, right? Those library will help you to trace, help you to, take the traces. That means execution orders. And then they send this log to some centralized dashboard, telemetry. And then you can see the actual flow of what each agent is trying to do. So that technique is called tracing technique, right? I mean, hopefully you have done that. So what this innovation or in this framework is doing is, they are basically claiming that when your agent is executing some task, they are able to trace their task. They're able to, they means here the lightning agent framework is able to track or trace your calls, and then later you provide a reward function. There will be RL based reward for that, and then all together it will able to start training your model in a feedback based loop. So that seems like a magical to us, but that's exactly the paper is going to show. Okay, so we'll go into that. So let's start with an example, same example. Okay. So what is it called is execution walkthrough. So again, what we are trying to do, if you pause for a moment, when you type this question in the chat bot, then agents get that. And then this is a complex walkthrough. It's not a simple RAG question. It has to walk through multiple steps, right? Here is a question coming here, right? Origin is the New York, and then destination is Paris. All the constraints are given. And then this is how typical agentic AI code that you developed is going to walk through. So if you look at here, it'll make a call to LLM and then say book a flight, right? I mean, basically, there are a few things we need to understand. So imagine this question goes through multiple steps. It's going to call LLM, it's going to call tool, and then parse the tool, and it might call the LLM. So there are 3 or 4 steps are involved in this reasoning process. So first step is call the LLM, right, with the parse request, right? Book a flight to the New York. And then, based on this LLM, because prior to that, you already told in your LLM call or you in your agent saying that these are the different tools available for your agent. So the LLM, I mean, your agentic framework, along with the tools definition, it's able to find out, oh, I need to get the next weekend. So let me call the tool called get dates. So, these are all already, I'm assuming you're familiar, how the agent and LLM and MCP tools are working together. I assume it's a foundation for this in this paper. So in which case it's able to figure out the tool to be used, and then it calls the get dates from the one of the tool, MCP tool. Then you in the reasoning process, you get the date for that get dates. Then it's going to call and now search for the flights. How do we search for the flights in this agentic application? You don't need LLM for that, right? You're going to call, of course, using the MCP, you're going to call some tool, called search for flights. It could be a Google search, or could be, some other provider who provides a search flights. Kayak may provide an MCP tool to return the search, right, based on the criteria. So your reasoning steps will call that. And then again, you may get the answer, saying that 4 flights found, and then next step is to find out which to book. So this way it continues. Let's imagine it continues like this. There is a call to LLM, there is a call to tool, and then comes back and then again calls to the LLM and then tool until it finishes. It's kind of the React framework that you might have heard. So what's the point here? The point here is, we are going through a trajectory. The concept I'm trying to set here is, this is called a trajectory. That is a core concept we need to understand in the context today. So when you ask a question to an AI agent, it is going through a trajectory. Now, is this trajectory is always the same? That's the question we are asking. This trajectory is nothing but imagine if you have a graph, there are multiple ways to reach the end. You can imagine like that, multiple paths to reach the source to destination. So apparently in AI agents, in LLMs, when you are using the LLMs are stochastic in nature. That means when you ask a same question next time, every time, it might answer differently, right? It is not a deterministic system. So any questions going to the LLM is a stochastic. The result might vary. So if you consider that in picture, your trajectories are going to be a different, many possibilities, right? There will be endless possibilities of trajectories out there. So now that is a crucial part of the problem. When to solve a complex problem, there are multiple trajectories, many ways of the steps involved. Which step is the best step is the question we are trying to answer, right? I mean, in the prompt-based approach, you don't have a control over that. If there are more trajectories are available, if you're only using the prompt-based approach, you cannot control that, desired trajectory for you, because there is a randomness in the possibilities. What people try to do, we try to put constraint, try to put in the prompt, it has to be within this or ignore. We all try to put constraint in the prompt in order to just select the best trajectory for us. At some point, it is not a desirable. That's where the fine tuning is needed. Now, with that context, the agentic lightning framework now is going to somehow simulate thousands of trajectories. When I go to the framework, the idea behind the agentic lightning framework is it's going to ask the same question, right, automatically many times. Right now I'm asking only one time. Imagine the framework will ask the same question and capture this trajectory. Okay, if it automatically does that, then it is a very interesting thing, because now these trajectories are becoming a source of training data. Okay, well, you will see an example later on. Okay, there are 4 trajectories here, right? In the first trajectory, we call rollout. That's a term used in the document. It is very successful. It is basically a good answer came from the trajectory, and in the reward we are going to give as positive, right? 1, for example. In the other trajectory, it over budget by 150. It resulted in a different number. Instead of 800, it probably 950. Because the way the trajectory went, it finally ended up in choosing the more, which is not desirable. So in this example, there are 2 trajectories are positive and the 2 trajectories are negative, right? Well, that's a great training information, right? If we can simulate these trajectories automatically through some technique, then if you can reward each trajectory automatically using the some technique, in this called GRPO, then you have a situation where you don't need to train manually, right? And then the system is able to simulate. In this case, agentic lightning is able to try different trajectories, and then also able to reward itself, and finally it's able to update the weights in the model. All can happen at the simultaneously by the framework. So that's the beauty of this framework's proposal. Well, can we do without this framework? Yes, you can do that. This framework is making it easy for us to do that. Without this framework, you need to write a code to simulate these trajectories, and you need to somehow make the reward function work properly for you. All those things are taken inside the framework. All right, so we are going to go into that details later, but this is the this is idea behind the paper, right? How a system can simulate trajectory, how it can reward itself, how it can fine-tune itself. Let me pause here, and before that, any questions, I will answer that, and before moving to the next topic.
Krishnan, you mentioned the framework automatically asks the question, but where are we adding that framework?
Yeah, that's a good question. So here is a thing, right? It is the architecture of the framework. If you look at here, where are we means, when we walk through the code, obviously I can easily point out, but right now we are in the diagram, right? But you can imagine like this, here is the Lightning server. This the Lightning server is actually running the LLM. Okay, when you actually deploy the code, you will be running a server called Lightning server, and that Lightning server is a library provided by the Microsoft. In that, there is a way to just connect to your LLM. If you are Qwen or if you are DeepSeek, you can connect to that. So that is this portion. And this Lightning server then provides a open compatible API. Okay, so then the whole thing becomes a local LLM API, right? Only thing is it has more components here. That's the first setup. In the right hand side is your client, which is an agent. Okay, it's a client wrapper, you can call. Then the client wrapper is run, and then apparently, let's say you have one agent. Let's call RAG agent. In this case, 3 agents are given, but let's say you have only one agent, which is the flight booking agent. Then flight booking agent, maybe there is an interface here to chatbot. This diagram is not showing that there is a chatbot here available to the end user connected to the RAG agent, right? Then you ask the question, book a flight to the New York to Paris. Then the RAG agent is going to make an API call to the local LLM through the API, right? And the Lightning server is the local LLM is going to respond. So this is happening. So imagine this is keep on happening. So while these are keep on happening, in the client side, there are more libraries are part of your Lightning client. it's going to generate trajectories. Okay, and then trajectories, which we are going to talk more later, is going to keep training the model. So, but I missed one point, which is like I was telling you, user is going to call the RAG agent, right? I mean, that's a normal behavior. But here, the task is the one which is simulated or synthesized by the Lightning server. It is going to ask the same question. You might want to tell the Lightning server, here are some sample questions, like a regular user does. You probably need to say that here. Once you say that to the Lightning store, it's going to keep on asking the same questions, what they call task, many, many times or multiple times. When you ask the same question as a task, then it's going to make a request and response. It's keep on happening. And then meantime, a trajectory based the reward data or training data will be created at some point as the runtime goes, and then it will also train the model. So this is the core of the problem, core of the paper. Once you understand that, of course, you can also read your paper on your own. Again, I want to pause here and then see we get it.
Krishna,
Yeah.
which part has the control of number of trajectories to be done here?
So this is controlled by number of that is the library is going to take care, right? So when you are given a task, right, for a given task there will be n number of trajectories, right? I mean we as a user or a programmer, we don't need to worry about that. That's basically taken care by the system. You can configure saying that I want to limit to only 5 trajectory, right, or 10 trajectory. So that is configurable option. Now, that's a next level detail, right? How many trajectories should I need it for a task? That is more like a hyperparameter experimentation, right? We need to find out. We'll come back to this diagram one more time, but I think it's a good diagram to keep in your mind. It's automatically it's going to train you, right? I'll train the model that we are talking. So now let's go deeper into see what is trajectory means. Then we get an understanding. Let's go here. Okay, I'm going to pause to before we go there. Let's go here. Where are we now? So, well, we talked about these things. Some of the challenges. It's kind of a summary. Some of the challenges in the regular agents are these are all the challenges. We reviewed that. And then the current architecture is we reviewed that, and this is all fine. Now this is let's build an agent. Okay, so now we need to little bit concept we need to introduce before we go deeper. We looked at so far from a block instead of system diagram, but what is RL and what is Markov decision process? These are very important concept. Theoretical background needed to understand the paper more. So reinforcement learning, right? You probably wait a minute. Probably wait. Okay. So I think that the theoretical foundation is the following, right? When it sounded easy as a block diagram, but what is a theoretical foundation? The theoretical foundation is LLM is in what is a Markov chain process, MDP. You might have heard about that, right? It's basically we are the current decision or current recommendation is not influenced by the past decisions. It is influenced, that means independent of the past events. When you make a new, when someone recommends, in this case LLM recommends, it is not past. It is not past. The LLM is not maintaining any history. It's a stateless, right? So from that perspective, when you make a call to LLM, it is not any of the LLM decisions or LLM recommendations is not dependent on any of your past decisions that LLM made. So that's a statement is made by the theoretical, which is true. We all know that LLM is a stateless. So in that situation, we need to understand what is a state, what is an action, what is a reward, because we are now going to fine tune a LLM, which has a property of Markov chain, right? Markov decision process, MDP. So in this situation, these are all not new concept. Over the time, robotics and then other, all kind of MLA technology. People thought about the state, right, and then action and reward, right? It's a old problem or old technique. But in the case of LLM, the way we need to visualize, the state is something we are giving into the LLM, right? Which means the system prompt, which means the user prompt and system prompt, right? And then the question that we are sending is the state. So the state contains all this information. Action is the response, the LLM tokens coming from the transformer model. So that is why it's the input to the LLM. The state is an input to the LLM, and action is the output from the LLM. And the reward, we are going to, based on that output, we are going to automatically calculate the reward. That's where GRPO is going to come in. Okay. And then what is policy means? Yeah, when you look at the paper has so many equations. The policy here means the LLM itself is a policy engine, right? Again, we are all using the same terminology in LLM context, but if you go back 10 years back, you might develop a policy engine. That policy engine will have multiple strategies that gives the right action, right? That's a concept in this prior LLM stage. But here, LLM itself is a complex policy engine machine. The transformer is a policy engine. So that's what it is. Trajectory means when you ask a question, it goes through multiple, we are asking a higher level questions, book a ticket to flight, right? That involves multiple steps and paths, calling the LLM tools, and then again come back. All together is called a trajectory. So that's a core concept we are talking. So rest of them a little bit details, but that is a foundation aspect of the paper. We are assuming it's a MDP state of the LLM, in which that's very important from theoretical foundation, because as later on when you apply the probability distribution, you're going to be realizing that's useful. Okay, so let me pause here and then let me go to one other page. So, okay, this is another important one. So now we are fully going into the reward model. So now we are going deeper into the ML training. So ML, a neural network model, has, obviously we know weights, right? It has so many neurons and weights. And when you train a model, you're going to update the weights of the model. Now, what the problem says, there is a statement called single turn world and then multi-turn reality. What does it mean? So what does it mean is, when you ask a question to your LLM, what's 22 plus 4 or 2 plus 2? It's a single path, right? It's not chain of prompts. It's a very simple question. The LLM would be able to quickly answer in one token. A couple of tokens, it tells you the answer. So, the question is, this is one type of situation. Other type of situation, which is what the problem context for this today. Agents is not a single type call, right? And when agents wants to achieve something, it has to do a lot more call. Again, we talked already. It has to call tools and LLMs and stuff like that. In this scenario, how do you train a model? So in this scenario, it's easy to train a model, right? I mean, many people, because there is no complexity. You ask a question and you look at the answer, and then you reward the answer, you train it. In the multi-turn, it's not easy. The reason is, when you're thinking about a reward, we want to know, who should, if the answer is, final answer is good, but how do I reward individual steps? Because, it making multiple calls to LLM, multiple calls to tool. How do I reward? Should I reward individual steps in a way that, you did a great job? Or should I reward only the final step, ignore all the individual steps? So there is a complexity of thinking about reward in the multi-steps, right? That is a problem. Again, this paper is trying to solve, or ideas from the paper is helping to solve. That is a core problem we all need to understand. When we are getting into the agentic AI LLM training, we need to realize that it's much more complex, because function level agentic workflow has so many steps, so many trajectories, and which trajectory should I reward, and then which trajectory, has multiple steps. You need to update multiple times the model. Okay. And how do we do that? If we don't have the technique to do that or understanding to do that, we are not going to be able to fine tune the LLM properly for our workflow needs, for the complex process needs. So that's a problem setup. That's called credit assignment problem. In the paper, you will see the word credit assignment over and over. So
You have a quick question if now's a good time to pause. Appreciate that. So when you scroll up, there's the reward state that is being evaluated. You have your reward, which tells the model what is good and what is bad. The piece I'm seeing is how is that evaluated? Is it through like LLM as a judge or?
Yeah. Yes, exactly. So LLM as a judge is one way to do that. And other way to do that is GRPO, which is a core concept here. It doesn't use LLM as a judge. It does, we need to know the final answer anyway. Okay. And there are 2 or 3 nuances into that. If the problem is, or the steps is a mathematical question, right? Then we can apply some calculator or some complex mathematical tools behind that to understand that the math question is correct or not, answer is correct or not. That's how the DeepSeek was doing it. DeepSeek was actually using mathematical reasoning without any human need to tag or reward all mathematical problem. So similarly, for coding problem, you can see, whether the coding actually created the correct result by running the code. So anyway, these are all the advanced techniques in which reward function is associated with validating your particular output, or in the coding case, it's a code output. In the case of math, it's a mathematical result. So in many cases, you would able to, without human judgment, you would able to validate the answer, and then you can create a reward. So that's one approach. Here, then what is the approach? Here also, if you look at, the same approach is followed, and then you would see that it's going to validate the results and it's going to assign a reward. Okay, right now I said that, and before the problem I was trying to put forward is the reward that we are going to associate here has to be not only based on the final answer, it has to be based on the multiple steps. Let's go into that and then come back and answer if you have any more questions. Is it okay? I'm going to visually show that.
Yeah, absolutely. It sounds like you answered it, because if the answer is whether it's going to be a reward or not. So I believe that's GRPO, but I'm sure you'll go into it. Thank you.
Correct. Yeah, reward is definitely needed. So let me see, I have a better visual on that before I go to that text note. Let me see here. If I have that better notes here, this a little bit detailed one, just bear with me. I'm just trying to see whether better representation is here. No, not yet. Okay, let's use this notepad. So I think the way to visualize, I think when you go to the paper is so condensed, it talks about mathematics. But before the mathematical problem, let's look at that one more details in the notes. Okay, I hope this will, yeah. Okay, I think this will make it easy. Okay, what are we talking? We are basically talking about walking through how the reward is defined or created for our problem ask. Here is a user question. Here, imagine that the Lightning framework is going to ask the question. Okay, I'm going into the root of the problem. Let me, yeah. 1 second. 1 second. I'll go to some place. All right. Okay, so I hope this might help a little bit of the diagram here. So one of the thing, if you look at that, here a little bit notations. Notation is T means time T1. Okay, we talk the same. Imagine the same question is asked. Imagine that same trajectory is being created. In this trajectory, we have, these are the steps. It's calling the LLM call, and then it's calling the tool. Again, it's calling the LLM. Again, some tool, search tool. Again, calling. So these are the sequence happening in this trajectory. Now we need to reward this trajectory. How do we reward the trajectory? So, by looking at the output, right? I mean, we can reward the trajectory. And then if the output is not favorable, we are going to say the whole trajectory is bad. If the output is favorable, now we are going to declare this trajectory is good, right? And that's what we are going to do. Let me see. I mean, I'm going to find out another easy way to see that. Let me see. All right. Okay. So, I know we need to say when we go to this level of details, we need to think in multiple direction. So here you can see that in the case of rollout K1, rollout is a trajectory. Both are synonyms. You are saying that the maximum price we are setting is 800. And then if the AI agent is able to get it from the 650, then we call it as a best, I think, reasoning, and then AI agent is able to get the best price. So that trajectory is the successful trajectory. All right. But if the agent in the next trajectory, because I told the trajectories are stochastic in process, right? And that's a foundational aspect. If you're trying to understand that, LLM calls sometimes give a different probability distribution. Somehow in this trajectory, you get to the $950, which is a failure, right? Which is over budget. So now you're going through 4 trajectories. I told you that these trajectories are automatically initiated by the lightning agent, right? Lightning agent task would ask the same question multiple times, which creates this trajectory. So you have 4, in this case, there are 4 trajectories are tried out, in which you have a couple of success and couple of failures. So right now, the system is able to create a trajectory, but it is not trained the model yet. As of now, it's able to, for a given task, it runs, let's say in our configuration files, we set 4 trajectory. You can also say 10 trajectory. So the system is able to, if you set 10 trajectory, run 10 trajectories, it's going to try 10 times. And then it's going to note all these success and failures. So what are we giving now? Now we are giving one label data. The label data is nothing but the maximum price. That's all we are giving. And we are not giving anything else. This trajectory is correct or this trajectory is bad. We are not giving that. All we are giving is the price, maximum price you can do. So that you can call it as a label data. But other than that, we are not labeling any of the trajectories. So that's a first understanding. Now, look at this way. Now let's say that now we are going to, this sequence of steps are going to prove you why GRPO based approach is better. I mean, you can pause me anytime, but this is a crucial part. So now we need to award. So what we are going to award is, right, if in the rewards we are going to give, when I say all the rollers succeed, we are going to reward. Imagine if all of them are successful, we are going to say 1, 1, 1 each, right? In this case, not all of them are successful. Only 2 of them are successful, 2 of them are failure. This is a reward system we are giving. Okay. So in this case, we are saying that, the first trajectory is 1, and then second trajectory is failed, and then similarly the third one is working. So we are giving that reward. So now we are saying is our reward is a range between 0 to 1. I mean, that's a decision we are making, right? I mean, later you are coming to know, sometimes you may need to give reward in a different range between 0 to 100. And depending upon the task, because when you're training an LLM, it's very crucial to know each task complexity is not same. Sometimes flight booking complexity, you can say that I'm going to reward between 0 to 1, which is not same as some medical emergency, for example. I'm just making up. So you cannot compress the reward between 0 to 1 in all use cases, right? Depending upon the task, depending upon the use case, the range might differ, right? You might think in my case it's 0 to 100. Then only I can able to reward properly. That's how you may decide for a given task. So just for a theoretical foundation, imagine that different types of task needs different types of ranges to reward. We need to make that as an important assumption. So when you have a situation where different task has a different range of reward function, it creates complexity. What is that? Because you cannot go to LLM and say during our model update training, these are all the rewards. These numbers will be later on will be used. If you're familiar with the way the weights are updated in the neural network, we basically do a loss calculation. In the last calculation, essentially, we are going to either reduce the weight, the number of the neuron, or increase the weight of that neuron, the probability of the neuron. So these are all part of the core ML weight updates, which anyway, I'm not going into the detail. But what we are trying to do is when we are doing that last calculation, we are going to be using this reward as a function, and then to derive how much weight should I increase or decrease for the neuron. So that is the part of the model training. Okay, let me pause here and then see whether it is going too deep or stay at the level we all understand.
I'm understanding it.
Okay.
What I'm curious about is, which you've lightly touched on, it might be implied, but like for example, you have all 4 rollouts succeeded, rewards
Yeah.
1, 1, 1. Is that array? Is that a trajectory? Is that correct?
Yeah, no, we are going to say it is not the way it is going to be. This is a stepping stones to say this is not the approach. They're just saying that this is one of the approach. We are not going to use this approach.
Oh,
But-
okay.
okay.
After.
Yeah.
Okay.
Right.
Got it. All right.
All right. So this is not the correct approach. So what approach this paper is going to say? Okay. So yeah. So now that is the core. One thing that we want to learn from today's topic is credit assignment, right? Credit assignment is the name over and over in the paper going on. So what is that? Let's go into that. This is the agentic lightning solution. The one I talked about is the regular way of doing it, which we are not going to touch it. So what is that we are going to do now? What we are going to say that is the credit assignment approach. Again, it's a lot of okay. If you could be able to visualize that, there are multiple steps in the trajectory, and each trajectory steps is the assumption here. The first assumption this paper is saying, you really cannot differentiate between the step 1 and step 2 or step 3. All steps are important to solve a problem. At the same time, the paper also recognize that in some cases, it's better, we can give a weightage based reward to each step, right? That's a crucial statement I'm making. Imagine there are n steps in the trajectory, right? And then in the first step, you may say first step is important. Some other task, the last step is important, right? So how do we decide then? Should we then somehow magically say based on the task, should we give reward to each step differently? Is the question asked in the paper. Or should we give equal weightage to all the steps in the trajectory? So these are foundational questions in the paper is asking. The authors are saying, let's start with the identical credit assignment. That means that if the final end result or outcome is favorable, then give equal weightage to each step. That is the first statement this paper is proposing. And then later on, it's going to say we can make a small tweak, not a major tweak, to give some preference to some steps. So basically, they're saying majority you give equal preference to all the steps. Then the question comes, is it the right approach? That's a critical question we are asking. If you are giving equal steps, equal reward to all the steps, is it fair? The paper claims that we are talking at one trajectory, we are giving equal steps, right? But if you're thinking as a training as a multiple trajectories, you're going to go 10 or 15 or 20 trajectories, right? But having equal distribution of the weightage actually benefits. That is the logic behind the identical credit assignment. Okay, I mean that I know we are going a little deeper, but that's a claim made here is give equal reward. When you say equal reward, if the final reward is favorable, give that benefit to all the steps. That's the bottom line here. Okay. Now, why identical credit works, right? The key insight. All right. So, we are continuing the same problem. I'm also looking at the time now, 8:14. So maybe, I will go through this a few more times and then I'll go into the paper. But the essence of paper, anyway, we are going to have another session, right? Because it's a deep paper. Today, I'm setting the concept and then context. And in the next session, I'm going to go probably more deeper into the paper and the code as well. But as I said, two concepts you want to take away today is the identical credit, right? And a little bit of the architecture. Okay, now we are saying that give equal reward to all the steps. Okay, so here in the rollout 1, we are saying that the reward is 1. In the rollout 2, it's a failure case because there is no, I'm not going to detail, but imagine rollout 2, which is the trajectory in the rollout 2 is not favorable. We are making it failure. And then let's say this is what's saying. Okay. Okay. This is a crucial statement. So even though the K4 means rollout 4, the search was good, but rollout failed. Basically in the steps, right? In between steps, every rollout has n steps. It may be possible that the first step is great, but in the last step is failed. Any reason could be that, the tool that you are using maybe not working at the time, or LLM stochastically giving different answer. Whatever reason is, the first steps are good, but the last steps are not fine, right? And then, that means, what does it mean? We want a collective reward to the whole steps, not the first step. So that is what this statement is making. And then now let's come to the crucial part of this. While we are right now saying that is the first statement is let's give same reward to all the steps. That is the most profound statement this paper is making. And then second step it's going to make. I think in our mind we need to wire this following concept. Every trajectory will have the proper rewards. Every step will have the reward. Now, some of you might be questioning, okay, fine. How are we connecting to the update of the model? Now, later on, there is another layer which we have not talked so far. That layer is the actual layer which is going to update the model, the neural network model, is going to go and consider each of this reward. While I'm talking, while I'm not showing it right now, but later on, the update weight program, which is going to be calculating the loss calculation, is going to come and look at individual rewards for each steps. Okay, that will come a little later. But right now I'm putting that context here. So awarding each step is a crucial step in this model training. Okay, I'm passing here. Let's say everybody get it. And then, I'm happy that everybody got the intuition behind that. And then I will tell the story of how this is going to be actually updating the weights later on. Yeah, any thoughts and any question? This statement that I'm making, imagine all the rollout is nothing but trajectory. Here are the steps. In this case, we derived here. So whatever I discussed, finally we derived to a state where, this is where our reward function stops here. Any questions on this? Anybody, sorry to ask. I just want to poll. Is it too much or too complex? Or I have not explained properly. So anybody can say anything?
What do we think, team?
Sorry?
I was just saying, what do we think, team?
Team, yes, yeah.
It
Yeah,
makes
because
sense. Honestly, I think when we see the code, it might be just a
all
little
right.
bit more clear.
Okay, so I think that's why it's a very involved topic, right? So I'm thinking how to proceed now. Is anybody understand this up to point? And at least
I just want to say, like in the rollout, if the last rollout is failed, so what are we doing? Like we are giving a cumulative reward, or like we are failing the entire step or something?
this rollout 4?
No, in the above one, the rollout search flight, yeah.
Yeah.
rollout failed, but the search was fine. So what are we actually doing in that case? I missed that point.
Yeah, we are not, we are, yeah. So basically, they are saying, right, they are not concluding anything here, right? So they are basically concluding averaging of the reward is not the, I think there is no conclusion here. So you can ignore that for now. I think the
Okay.
crucial, yeah, let me pause. This is the crucial one where we now arrived at the stage in the process for each rollout, we calculated the reward. And then this is the, I think we can stay on that, right? And this is the crucial part. Okay. I mean, I'm thinking how to proceed now. So, I mean, let me connect the dots here, right? I mean, let me pause and then I know we are different type of people are here.
Yeah.
So,
So just to kind of
yeah,
recap what I understand, and you
yeah.
can tell me if I'm wrong or not.
Okay.
Basically, you have like let's say you have rollout 1, and you have your for each value in the array there, you have a
Yeah.
success or you have a failure.
Right.
One of the claims of the paper, which is actually very interesting, is that you don't wait one step in your trajectory as higher or lower. You make them
Yeah.
the same, which is
Yes.
very interesting. So then when you have each state in your trajectory, or like each step when you're booking a flight, you
Yeah.
assign what's going to be success and what's going to be a failure.
Yeah.
And so in the first rollout, in that trajectory, I believe that's a trajectory,
Yeah.
you have everything wins. You had everything that went very well, so you assign a 1.
Yeah.
And then what happens is then you have your set of your trajectories if they succeeded or failed, and you put it into the neural network. It'll update the weights, and then over time it'll
Yeah.
converge. Is that correct?
Exactly. Absolutely correct. You're spot on. Yes, that is that we are not tied that yet. Yes, that is a point here. Uh, later when we take this reward, then we go a little bit more deeper on, figuring out the weights, updates, and all. We'll do that, but the intuition is correct. And then the intuition is, sometimes, for example, this step may be, not favorable. So, what the paper is trying to say, a lot of times because of the stochastic nature, the intermediate step may be not a great step, but final answer happen to be correct, right? That's a possibility. In that case, you're going to give 1 anyway to the step which is not done a great job, but since the final output is great, you're saying, okay, I'll give you that, right? But that is a crucial understanding. And then you're asking as a critic, one of the step is not doing good, then but why are you giving the same reward? You might ask the question, right? But that is taken care in a different way in the next rollout. If all in the second step is doing the same, not great, but overall is a failure, the model is starting to understand. In the first trajectory, though the second step is not great, but overall is win, let me give kudos to everyone. But in the second scenario, right, and everything is failed, and I'm going to make less favorable. In the third scenario and then fourth scenario, let's say the second step was great, some other step, right? I mean, then it's going to prefer the scenario where the second step is favorable, right, in its probability distribution. So over the time, over the many rollouts, the first question, the critical question you asked, right? Why we are giving 1 to a non-favorable steps is taken care in the large run of your training. So that's a crucial understanding. Am I making sense? Maybe I don't know how to show an example, but that's what the paper is trying to say that. I mean, whoever asked the question, did you get that intuition I was trying to say?
So you're saying the critical question is, I'm looking
Let's
for
say, let me pause it again, right? This step 2, I'm just highlighting here, right? Let's say the rollout 1, and then this is step 2,
yeah.
right? So the step 2 is about going to some tool and then let's say get the price, right?
Mhm.
Or get the flights, right? For example. But the in one scenario, that it that return 10 flights, but it is not great choice. Okay, I mean ideally you would say that step is not doing great. No, I'm not giving the right example, but I'm making it more abstract. So in one of the scenario, one of the trajectory, even if some of the steps are not great, But if the end result is great, we are giving a great result to the steps, right? That's what the paper is claiming. We all agree to that, right? No, it doesn't make sense.
So you're saying, okay, so like in the second step, it goes to fetch the flights.
Yeah.
Let's say it,
Okay,
I
I'm
don't-
going.
but let's say it turns an error but then it does it again and it succeeds. And
Yeah.
then and then that means even though it succeeds, it's going to be weighted at 1 because it
Yeah.
successfully completed. Is that what you mean?
Exactly. That's what I mean. Yes, that's one way. Yeah, that is your example is probably correct. It has to say that may be a great example. In the second step, it has to retry 5 times, 6 times, right? And then because of that, it went slow. But we are rewarding that. Let's say it's calling some API. That API is need to call multiple times. Though the reward for the step is we are going to be giving less because you took so much time, right? You retried many times. You're not doing great. But since the overall outcome is great, anyway, I'm going to give you the full reward. So that's the crux of the whole paper, right? But what I'm saying is, we all understand what's happening, but the critical question is, why would you favor great reward for some steps which is struggle to get it, right? Why would you favor? That is a critical question.
Yeah, why is that?
Yeah. So that comes to the nature of, you have to see the rollout in batches and how that batch is applied to the neural network, and then overall how it learns. So that's maybe I'll try to come up with an example, but the answer given to that is, some other steps in some other rollout, right? Some other rollout, in the failure rollout, if the same step 2 has that problem again, then in the overall, that the step 2 which we are talking, right, over the time it will be unfavored. Okay, these are you intuitionally you can understand, right? If the same step 2 appeared in the negative case, failure case, if it happened many times in the training data, in model will understand I should not use a step 2. I don't know whether I am saying it correctly.
That makes sense. I mean, like it's just you have these like weighted averages
Yeah,
effectively.
exactly. So that's another way to say it. Over the time, in the probability distribution, the step that failed in the successful scenario also will not show up. Someone with a better step will show up in the higher probability range.
So
Okay.
then when it's successful, it'll then outweigh like the weight
Yeah, correct. Yes, yeah.
outweigh the bad
Yes.
rollout.
Bad ones. The bad ones will go down. So I think we are not showing all those. It's impossible to show. I had to show hundreds of rollouts and then show that the one with the best favorable rollout will come in the top of probability distribution. That's intuition we need to develop. But right now, that is something I need to. I cannot show you, right? That's intuition we need to develop.
That a human like would develop each step, or is this automated? Like each rollout is automated?
Each rollout is automated. What does it mean?
Yeah, so what I'm missing is that like we assign credits to each step. So rollout 1 is 100% all the way through. But we're on rollout 4, that's 5 steps. So we added a step. A human is adding that step to see if it's going to be successful. Is that correct?
Oh, that one I was not paying attention. Yes. Yeah, you can say that, right? In the rollout 4, you can do that. Yeah. I think to make it simplification, don't, just because everybody is trying to understand, and let's forget about that. Just imagine, yeah, you're right. But for now, every step, every rollout can have multiple steps, right? But right now we are focusing on weightage only right now. I mean, that's a focus right now. I'll come to your point a little later. But we are trying to summarize today with the time almost 8:30. So let's pause here and then ask the team members here. So because we'll do it in 2 classes, right, or 2 sessions, so that it's going into our process properly. So let's go to the paper. We are going to do it in 2 steps. So now next week I will also go into that. Today, what did we discuss? Better to summarize what we learned so far, and then again go into deeper next step. All right, next session. Is it okay, guys? So that we observe, all of us observe together, right? Some of us are still probably trying to figure it out where we are, but it's very, very important paper. Let me rephrase where we are. If you look at the paper, okay, first thing I wanted to show you is the diagram I showed you a while back. And I'm going back to what did we discuss is, okay, maybe this one, or 1 second. I'm going to the right one, agent. Okay, this is I think this is an important high level understanding we need to have before we go too deep into that. So what's a high level understanding? Again, I'm summarizing for the purpose of other members who are trying to catch up with us. So what we are trying to say is agentic AI is very important now. And then part of that is fine tuning the LLMs used by the AI agents is becoming critical. Why it is becoming critical is today's agentic AI using most of the prompt based approach to solve complex problems, multi-steps problems. And it's quite possible that while in some cases prompt based approach might be sufficient, or even most cases, in some cases where there is a different data distribution than the LLM has currently, might force your prompt based approach to work not properly all the time, and then you will be tweaking the prompt and adding constraint, putting the so many things in the prompt which is eventually going to break. In such situation, we end up doing the fine tuning of LLMs or local LLMs. That's the first statement. Okay, now if you are still sort of trying to understand that statement, obviously we need to go much deeper, right, to make sure we all understand. But assuming that we understand that basic assumption, now the question is, how do we fine tune? There are many ways to fine tune. One of the few ways I showed you, the SFT, and then right, RLHF, and then DPO and PPO. These are all the techniques used mainly for fine tuning a foundational model or large models. And those things may not be even workable for agentic fine tuning. So that's a crucial statement I'm making, right? The fine tuning approach used by the foundational model training, okay, it could be still used for your agentic LLM training, but it may not be the best. Why? Why is that? If you take a traditional fine tuning, usually it is a single step process. I mean, now there is a chain of thought process DeepSeek is using in either a single step based oral fine tuning or even SFT fine tuning, right? I mean, it has limitations. So as the complexity of a reasoning process increases, especially in the agentic world, there is a concept of multiple calls to LLM and then multiple calls to tools. Now, fine tuning on what? It is interesting, right? When you have single question and answer, you can create a reward model. But if your question has so many trajectory, so many paths, then fine tuning itself is a complex process. How do I fine tune? How do I know which steps of the process need to be fine tuned? In this case, let's say we call it as a trajectory. When there is so many trajectories are possible, which trajectory should I favor? And then how, sometimes trajectories may come close, right? Sometimes steps in the trajectories all need to be taken care. When I fine tune the model, all these things need to be considered. So that's another level of understanding. So that's a problem, right? If again, that's a crucial understanding we need to have. When the agentic world, when there are so many trajectories are there for a given task, right? What is the meaning of fine tuning, and how do we fine tuning? So that's a problem statement. I think I want to pause here because once we and then we went to some small introduction to the weightage and then reward and then credit assignment, right? Those are all the next level details. So let me again pause in the beginning introduction level and then say, now that we need to do the trajectory based fine tuning, this framework is providing some of the nice way to do that. We don't need to do a lot of coding. So that's a technology part or framework part we can call. But the theoretical foundation is the trajectories are the key way to fine tune a agentic based LLM. So that's with that statement, I want to end here. Then we'll continue from the next session. So let me pause here and then ask questions or wait for the questions from everyone. I hope I didn't go too deeper today, right? I wanted to stay at high level. So I wanted to, if you don't mind, anybody else can, Murali or Ram, can you guys provide your view? What's your understanding? And then how do you want me to proceed next time? Any feedback would be great. And I want to know audience feedback, right? It's too much or too confusing or it's not deep enough.
ठीक होता ऑयल लगने से भी ठीक होता नहीं तो
Yeah. Okay. So anybody else other than who talked to the previously? I forgot the name.
I mean, most likely we'll be seeing some demo next week, right? That will be like make it easier to follow.
This is, may I know who is, I want to know the name, who is talking.
Sangeeta from Agents Class, Krishna.
Oh, Sangeeta. Okay, cool. So I'm going to talk about this in Agents Class also. We can talk about it.
Okay. Thank you.
Right. So other than Sangeeta, anybody else has any question?
I just want to finalize what a trajectory is here, how it's defined. Is it based, like if you think of the flight booking scenario, let's say it takes 4 steps to book a flight, that's considered a trajectory, right?
Absolutely. Yes. That's a trajectory. And maybe I'll show you next time, actual trajectories, right? I mean, I know it's easier for, to show me all the trajectories, right? Then I understand. I mean, that's the easier part. But now we are talking a little bit of paper-oriented theoretical foundation, right? Obviously, the practical part is easy for us to understand, right? But the paper reading always involves understanding the foundation through mathematics, but not all of us are mathematically savvy, but this gives some theoretical foundation, visual foundation. And then next week I'll go into the more theoretical foundation. Okay, so at least tell me whether next time we should go or not. I don't have any, I mean, if there are not many interests, I don't want to go into that. Sangeeta, we can cover with you later, but anybody else has any other questions? No?
Hi, my name is Murli, and I think I liked your example and walking through a real case study, and I think that's pretty useful. I mean, I came in late, so I don't understand the full architecture walkthrough of the case study, but it seemed a good way of reading the paper and mostly leaning towards the practical side. As a practitioner, that's much more useful, and also illustrates the finer details for a person to implement those and see where the issues are. Definitely appreciate that.
Yeah, by the way, thank you. But it's good that this paper has both theoretical aspect. Not many paper have practical aspect. But if you go here, which is what I'm going to go through, it's nice. This is a very good paper as well as a code. You can always go to this code, which I'm going to go through. I like this because of that. Many papers don't have a code or practical, but this one definitely has. We'll go into this, obviously these things and ask more. If you look down further, if you look at the, the way the paper first understanding, you look at this, this means nothing but trajectories running, though it is, they call mathematically, what it means is for a given input X and then a kth execution, that means the rollout, and there are multiple calls to LLM. There are one to many calls to LLM. So that's what they are trying to mathematically formalize, which is what I was trying to show visually and then step-by-step fashion. So once we understand a little bit of the visual understanding, some of us can understand the mathematical part of that. So we will attack the mathematics at the end. for a lot of engineers, first is the practical aspect and then the mathematical aspect. So in support vector, there are two. Our instructor Asif will take care of obviously mathematical oriented more. I am more of engineering perspective, so I'll start from engineering and then cover the mathematics. All right, so we are going to cover this paper in detail, but please do read about the paper. And then the takeaway today is the one that I was saying. Try to visualize the server and Lightning architecture and then benefits of this. And then the way the trajectories are going to be used to self fine-tune. If you want to use the word self fine-tune or fine-tune, anything is fine. That's a crucial aspect of that. And then details about how the loss functions is created using that approach of providing a similar weightage to each step in the process, and then how that mathematically the loss calculation is calculated is I'll put it in the next week, right? Okay, then thank you everyone. And then if you have any feedback, please do provide the feedback if you like it in the meetup. Thank you. Thanks guys.